I mean, Liz, Liz, Devin, do you see what looks like SQL on the screen there?
Yes, I do.
All right, excellent. Well, I want to welcome everybody to the to today's webinar. I know we've been putting on a few of these 26 SQL Server 2016 webinars, and there's just a host of really cool things that are out in 2016. Well, it's not a huge jump from a SQL standpoint, but there's a lot of other functionality that is a significant improvement. And in my world, the advanced analytics world, the biggest piece of this is obviously uh, uh, the R integration into SQL Server. And it's a really cool tool. And I'll show you why here when we get towards near the end of this. One of the biggest pieces that makes it so significant is the ability to move your models into the database. Rather than in traditional analytics environments, people have to take the data from the database and move it to their analytics environment and then do the R model or the modeling against it there. And so moving that data around can be a significant burden, especially if you're talking about terabytes of data or just very large amounts of data. In addition, no platform. So I came up as a BI developer and made that transition over to the advanced analytics or the data science world. But my core development background is in SQL. That is probably my #1 language is SQL, writing SQL. SQL is, in my opinion, by far the most powerful data manipulation language or tool there is. So if you've got data in a SQL database, if you're going to do some sort of manipulation to it, aggregating or transforming or anything like that, SQL far outperforms all the other tools. Now, you get into some of the big data world where you've got thousands or hundreds of thousands of log files in a Hadoop environment. It's a little bit different, but the vast majority of the data that we're going to model in the real world is going to come out of databases. So what R allows you to do, or what R server allows you to do, is push that functionality back into the database, and as well from the deployment standpoint. And again, we'll get to that at the end. But what I want to talk about here, so if I did a past seminar where we did forecasting taxi demand a couple months ago, and essentially, so if you attended that, some of this is going to look familiar. We did most of the data manipulation in SQL Server, but we did it in an Azure data warehouse, and we did the modeling in Azure machine learning. So in this seminar or webinar, we're going to do all of that stuff. We're going to do it in a regular SQL Server 2016 Enterprise Edition, and then we're going to do all the modeling in R. And I'm going to step you through all that and sort of show you what's happening there. So just an FYI, this is an Azure VM. And it's just a standard DS12 V2 with 4 cores and 28 gigs of RAM, and it's SQL Server 2016 RTM version, Enterprise Edition, I should say. So the only reason I went with it, so you don't need Enterprise to do the R server piece of it, but I was doing some stuff with column store indexing and that sort of stuff, so I needed the Enterprise version. So the cool thing, I was able to spin it up in just a matter of minutes, and then I've transferred all my data and scripts over here. So what we're looking at right now is a taxi database, and this is a database that is freely available on the web. And what it is, it comes basically with 2 tables: this taxi fare table and this taxi trip table. And what that is for the year 2013, they recorded all the trips, all the taxi cab rides within New York City, specifically within Manhattan, but there are some outer boroughs. And so this taxi trip table represents all the trips, so the lat long of the pickup and the lat long of the drop-off, as well as the time and the number of passengers and that sort of thing. And then this New York City taxi fare table has the associated fare that was, any of the fees or taxes or tolls or tips, that kind of stuff like that. And both of these tables are roughly 178 million transactions apiece. So it's not as small. They're not small tables, but they're not gigantic. I mean, we're not dealing with terabytes here, but still pretty good size. And so what I wanted to do was forecast taxi demand by the hour with a 5-hour lead time. So essentially, I wanted to build a predictive model that could tell me with some sort of accuracy what the taxi demand is going to be 5 hours from now. So if I was a dispatcher and I was trying to figure out how many taxis I wanted to have on the road, if I needed to call up any extra drivers, or if I need to take anybody off the road, sort of helps me as a taxi company with the ability to forecast how many tabs I need to have on the road at any one time. So it lets me sort of plan this out so I can better match forecast and demand. So I pulled it initially from this taxi trip table right here. So if we look at this guy right here, this is just the top 1,000 rows, and essentially just have, again, it has each record in this table indicates a taxi trip, pickup time, drop off date time, the latitude and longitude of where it was picked up, how long it took, all that sort of stuff. So what I wanted to do was create a simple forecasting model. And so I simply aggregated all those up into counts by hour. So the concept was, I wanted to be able to, I wanted to be able to identify for each hour of each day for the entire year, what were the actual number of pickups. And it's not a perfect design, but the concept was I wanted to have it create a table that looks like, it's called pickups by hour. And essentially what it is it has, so each record in this table is an hour within the year and the number of pickups. In this case, for March 17th at the midnight hour, there were 33,000 pickups. And so I created this whole table right here, and I've got this this script right here. Essentially, there's nothing fancy about this. It's just SQL, right? And so all I'm doing is just doing an aggregation, and I'm pulling it all together. I'm cleaning up the data a little bit as well, because there are some missing data points. And so in the data science process, not only do we have to transform our data normally from its transactional state, but to a more machine learnable format. In addition, I also have to deal with erroneous data. So if I didn't have any taxi cab rides for a particular day of the year 2013, I would think that would be some sort of error. If you've ever been in New York, you know, there's always cabs going somewhere. So part of this process is I'm trying to clean up the data and get it all in a nice format that I can use. And so this is the end result right here. So I've got it, this is a simple aggregation. I've got the date time that was picked up. And remember, I'm trying to do a 5-hour forecast. So this is my target date right here. So if in this particular case, this is 3 a.m. on March 21st, my target date that I'm attempting to forecast is 8 a.m., okay? And so what I end up with is this aggregation table right here, which just doesn't have a lot of features in it. It's got a lot of rows, but not a lot of features. So when I'm doing machine learning, the more stuff I can learn, or the more features or columns I give the machine learning model, the more it can learn from. In this case, all I would be giving it would be the target pickup hour and the target pickup day of the week, which in this particular forecasting solution it's not bad. I mean, if you know for a particular 8 a.m. on a Monday is going to be very busy in New York City. 11 a.m. on a Wednesday is going to be less busy, but it's probably still busy. Or Saturday night at 1 a.m. is probably going to be very busy, but Saturday night at Saturday morning at 1 a.m. But Saturday morning at say 4:30 or 5 a.m. is going to be less busy, right? So we can infer something from that. But what we don't have, we want some additional features that we can use to learn from. And so I've created a second table, which is this lag table right here. So it looks similar to that first table. And this is going to be the table that we learn from. This is going to be the one that we're going to feed into R. And so what this has, in addition to the target pickup hour and the target pickup day of the week, we also have some lag numbers in here. So what we end up doing is we end up lagging back. And if I look at this guy here, this is the SQL. So if you guys are familiar with the lag functions or the windowing functions in SQL Server, they're incredibly powerful. They weren't always there, but they've been there for a couple of versions, and they're super powerful because they let you do stuff from an analytics standpoint that you couldn't do in SQL, or was very difficult to do in SQL previous. And a lot of this stuff you had to do in, say analysis services or some other tool like Python or in R for that matter. But what ends up happening is that I end up creating this table right here with all these lag features. Now, some of these are null at the very beginning because the very first day we don't have backward data. But I've created a set of features, and based on the current hour, so if it's 5 a.m., I'm trying to predict what the taxi cab demand is going to be at 8 a.m. And so what I'm going to use is some of these lag functions right here. So this is lag 0, lag 1. So these are how many hours, what the demand was 1 hour ago, or 2 hours ago, or 3 hours ago, or 4 hours ago, all the way through 7 hours ago. And then in addition to the hour lags, I've also created day lag. What was the demand 1 day ago, 2 days ago, 3 days ago? So what I'm trying to do, I'm trying to build a model that can forecast the demand 5 hours from now based on what the day and the day of the week and the hour is going to be in 5 hours, but also what was my historical demand leading up to it. So is there anything that I can learn? So there's a lot of stuff that happens in New York that I don't have access to. I don't know if there's a big game or a sports event or a concert or some sort of a conference or something going on. So I don't necessarily have access to that kind of information in my data. But if I build these lag features, I can see that historic demand 3 hours ago or 3 days ago was very, very high, higher than normal. So I'm going to adjust my forecast based on it. So it just kind of lets me, sort of a poor man's way, to be able to see is the demand, the most recent demand, is that somehow correlated to the future demand here. So and in truth, that's normally how these things play out. For example, a stock price 1 hour ago is going to be correlated somewhat to the stock price in an hour from now. So anyways, I do this, and what I've done is I've taken that pickup data that had lat, lon, and hack ID and all sorts of stuff, and I've transformed this into a machine learning data model, which what we have right here. And each row in this table represents an hour in the year. So now that I have this data, I'm going to come over to R. All right, now what we're looking at is this is a programming tool called RStudio, and it's just a GUI on top of the R programming language. And Microsoft also has their Visual Studio, so there's a version of Visual Studio that's R tools for Visual Studio, and it's pretty good. It's fairly new. You can use either one, so the environment doesn't really make a difference. The code is exactly the same. So what I'm going to do is I'm going to use a version of R. So Microsoft makes 2 versions of R available. They make a free version available, which is called Microsoft R Open, and then they have a not free or part of Microsoft R Enterprise, right? Which is what I'm using here. But I could have used R Open as well. There's some features in here I'll talk to you about here in a second that are specific to R Enterprise. But one of the problems with R, regular R, the open source R, it's an open source tool set. One of the issues with it is its scalability. It's an in-memory tool, which means that in order to analyze data or to build models against data, you need to bring all that data into memory. And if you have a limited amount of memory on your machine, you can only bring in so much data. So if you're trying to model, say, a terabyte of data, you're not going to be able to bring all that into memory. Most of us don't have a terabyte of RAM. So the counter to that is Microsoft Enterprise, which allows you to not necessarily have to bring all the data into memory. It allows you to chunk in data a piece at a time and then do the analysis and then remove that data from memory. So in theory, you could iterate over a petabyte of data in our server, even though you only had, say, 24 gigs of RAM on the machine. So what's happening here, and I don't want to get too deep into this because R can be a little confusing, a little overwhelming if you're not familiar with it. But essentially, what I'm doing in here is I'm setting up a connection to this SQL Server, and I'm creating 2 different data sets here through this whole process right here. I'm creating 2 different data sets. One is my training data set, which is this guy right here, and one is my testing data set. I am going to build a model off of this training data set, and then I'm going to evaluate how accurate that model is here from this testing data set. And so all I'm doing is I'm using these RX functions right here in R, right? And so this is part of R enterprise. And what's happening is that it is doing all the analysis. So even though I'm doing this on a client machine, all the analysis is going to take place inside the SQL Server database engine. Well, it's not in the database engine, but it's going to happen with, I guess within the database engine. But what happens is SQL Server is going to shell that out to an R script. So I could have the database could reside in a data center the other side of the world, and I could have this on my Surface here at home in Florida, and I could do the analysis. And whenever I click the button, what's happening is that rather than bringing the data to my client, it's sending the analysis to the SQL Server, and then SQL Server is going to turn that into a number of SQL statements and that sort of stuff, and it's going to do all that analysis at the SQL Server, which in theory should be a lot larger, more powerful than my Surface, and then it's going to bring it all back to me all nice and tidied up. So for example, on the train data set, right, and what's the train table is going to be this view right here, which is basically a version of that table I was just showing you with all the lags in it. So if I go ahead and click on this run button right here, what's going to happen here is that it goes back to the database and just essentially brings back all the metadata for that table, so I can take a look at it and see what's happening there. All right, so one of the things you do when you set this up, there's a number of installation steps, but you also have to have a local share on your machine. Even though it doesn't necessarily bring the data back, you set up a share on your machine, so if it has to do any intermediate processing in your local directory, you can do that there. If the database doesn't exist, I'm going to create it. And here's where I'm creating a SQL Server compute context. So this is what I'm going to use this is where I'm going to tell it to do all of its calculations. So I create the compute context right here, and then I set my local environment point to this SQL Server compute context. If I wanted my analysis to happen within my machine, I would set that compute context to local. If I wanted to change it so to do all the computations back in the SQL Server, I set up that way. So all I'm doing is just changing my context one way or another. And where I would want to do where I would want it to happen locally is that because this is R and I have to respect the open source nature of R, there are a lot of packages that are written outside the world of Microsoft. Matter of fact, the vast majority of them have no recognition of SQL Server or anything like that. So there's some advanced scientific models. There's some really cool machine learning algorithms like extreme gradient boosting or whatever. There's a ton of different neural networks and that kind of stuff. So not everything is able to execute within the SQL Server environment. So if there is some special algorithm that I want to use, I can bring the data back to my local machine and process it in there as well. So I can have it where I compute locally or within SQL Server. So there's a number of functions that are available. Everything RX within R is related to the R server. Right? It used to be Revolution Analytics, but now it's R server. And for example, I can build a histogram right here across that table. And so what's happening right now when I run this guy right here, what it's doing is it's sending a bunch of instructions back to the SQL Server, and the SQL Server is going to execute the histogram for me, the visualization, and then bring it back to my desktop. So very, very small percentage of this occurred on my machine. The vast majority of this occurred on the SQL Server. So I can do a ton of different visualizations within just R. Now, within the SQL Server. Now, there are a lot of custom visualizations like ggplot2 and some other sort of more advanced scientific type stuff. If you need to do that stuff, you can't execute it on the SQL Server, but you can bring the data back to your environment and then execute it within any package that's freely available within R. So here's a function right here within R. This is a summary. So if you guys are familiar with machine learning, you've seen it before where we've done what we call exploratory data analysis. So we want to understand the mins and the maxes and the standard deviations and all that sort of stuff. If I run this RX summary right here, I basically can, for whatever I put in there, so here's my formula. I'm doing it for target pickup hour, target pickup day of the week, and the number of pickups for the training day, which is a view that's pointing to that SQL Server table. And you can see what's happening here is, for example, target pickups, that's a numerical value. And I can get my mean and my standard deviations and my mins and my maxes and all that sort of stuff. And pickup hour and pickup day of the week, those are what we call factors or categorical variables. So it's just showing me that, you know, like I would expect, there's 24 hours in a day, or 24 hours in a day, 0 through 23, as well as 7 days. And it gives me the count, the number of records for each of these individual observations. But if I was going to do this from scratch, there would be a lot more analysis that I'd want to do here, because I want to fully understand my data before I do any sort of modeling. All right, this is going to be my modeling formula right here. So what this is telling me is that I am going to build a model with an attempt to forecast target pickups, right? So that's what I want. That's what I'm forecasting my pickups to be 5 hours from now. And I'm going to, so I want the algorithm to learn, right? So I want it to learn all this stuff right here based on, so for example, the target pickup hour, the target pickup, the day of the week, I want all the lags in there as well. And so can I find some sort of hidden pattern in the way all the data oscillates within those buckets that's going to create some sort of formula that's useful at forecasting this target pickups. So I create this formula right here, and then I'm going to pass it to this function right here, which is linmod, or if you're familiar with linear regression, essentially that's what that's going to do. And so here's my formula. That's basically this, this guy right here. And then I'm going to say, apply this formula to this training data right here and generate a multiple linear regression and save it in this LM function right there. So if I've already run it. So if I do the summary for this guy, I can see the output of this. Here's the output for the linear regression. And what it does is it brings back, because pickup hour is a factor, it breaks it into its individual little fields, right? So it's going to create a coefficient. So a coefficient would be something that I would multiply the number by. So basically what happens is that I use this estimate column right here to generate a formula. Okay, even though I don't do it, R is doing it for me. So we've got this whole formula right here. And it also, one of the cool things about R that you can't do in Azure ML is you can see statistical significance of each one of these coefficients right here. And so the dots mean it's statistically significant. If there are no dots, it means it's not significant. I wouldn't worry about it too much in this context, but if I had a bunch of like individual like features and that, you know, taxi cab rider's hair color or something like that, I'd want to sort of analyze that for statistical significance to see if I want to add it into the model or not. So anyways, we generate this model, right? We don't really care what it's about. We do care, but for the sake of this, we're not too interested in what it is. We just want it to make predictions for us, right? So we generate this model and we save it into this LM object, which stands for linear model. Now that we have this linear model, what we want to do is we want to score the data, and that's what this prediction function right here does. So we pass it in the linear model, in this case the model, and then we pass it in our training data, right? Okay, so I'm doing two predictions. I'm gonna predict the data. I'm gonna predict the training data, which is the data I use to develop the model. I'm gonna predict it and see how close it is actual versus actual value versus forecasted value. And I am going to save that into this table right here. This is a SQL Server table. It's called pickups underscore train, or pickups underscore score train linear, or LM for linear model. So this is the training data. Now this is fine. This is just for demonstration purposes. What we're more interested in is the next chunk of code down that we call our testing data. So what I'm doing is I'm setting up a table, and I'm creating a data set. In this case, it's the score train data set, which is essentially pointing, this is a pointer that's pointing to this table in SQL Server. And all I'm saying, if it exists, go ahead and drop it. Otherwise, because this is going to recreate it every time I run it. And so when I run this guy, I'm going to do a predict function. I'm going to pass in the linear model, the input data, which is this training data, the output data, which is this data set that points to this table. So it's going to do the prediction, and it's going to put it in this table right here. And some other variables, don't worry too much about that. Now we're also going to come down here and do it for the test data. So this is much more important than the training data. I would expect that a model could memorize the training data and then do a pretty good job of making predictions from the data that it just memorized. But what I'm also going to do is I'm going to take a certain amount of that data, I'm going to hold it out. So I'm not going to show the training process every piece of data that I have. I'm just going to show it a piece of it. And then what we call this, then I have another testing set of data, which we're going to call out of sample data, that the model has never seen before, and now I'm going to give it that. And I already know the outcome of this testing data. I already know what the actual pickups were for those time frames, but I want to see if the model, how well, I want the model to make its predictions, and I want to compare it to see how well it did. And so essentially that's another predict function right here. And then what happens is that data gets written out to this table right here. So here's the output of the training data. So when I predicted the function against the linear model for the training data, so in the base table I have an ID for each record just so I can keep track of what goes with what. But here is for example, the very first record had an actual pickup of 4,000 and a forecasted pickup of 3,200. And then the next one had an actual pickups of 11,000 and a forecasted of 9, and so on and so forth. So, and I have about 1,400 predictions that I made. I'm not showing all of them right now. But what I need to be able to do is I need to be able to evaluate that to see how well it did, right? So I have something here, and I'm trying to do as much of this I can in SQL, right? And we'll get to the very end. You can see that I did pretty much everything in SQL. So you don't, the point of this is that you don't have to be a guru in R, right? If you're a guru in SQL Server, you're already about 80% of the way there. All right, so what I've done here, if you've ever heard of the coefficient of determination, or R squared, that's a measurement or a metric by which we determine how well, in this case a regression or forecasting model, how accurate it is, how well it actually predicted the actual values. And so essentially what happens is that we do this sort of math right here, and we take the forecasted pickups and we subtract the targeted pickups, and we square it, and we sum it up, and then we compare it to what we would call here would be sort of a null model, right? So let me go ahead and run this guy. And I am doing it, actually, I'm going to do it just for the, this is just for the training data for the linear model. And so what we're looking at here is a score of 77, right? Which indicates that the model from the training data was able to forecast roughly 77% of the data. So this value should go from a 0 to a 1, and a 1 would be a perfect model. In this case, a 77. That's not actually that bad in the real world. If we were doing something that was useful, that would be a score, although we would try to improve it. But this is the training data, and it's not really relevant. What we want to do is we want to evaluate the testing data, right? And that's what, so if we look here, we're pulling the data from the train, but here we're pulling it from the test. So our training score was a 77, and our testing score was a 72. So that's still pretty good. I would expect my test data to be a little bit less than my training data. It doesn't always happen. There's some sort of random occurrences in the data that can often lead to the testing data being a little bit better than the training data. But for the most part, I would expect my model to do very well on the training data, because that's the data that it used to learn and build the model. This data right here, this test data, is data that the model has never seen before. And so I'm just telling it, here's some data you've never seen before, go ahead and score it. And so we ended up with is a 72. Again, not a bad score, and in the real world, it would probably be, you know, fairly useful. So now let's go back to R. That's a pretty good model, but it's a linear model, which can sometimes have some limitations if the data you're dealing with isn't fully linear. And don't worry about what that means, but sometimes there are patterns in the data that you can't necessarily plot with a straight line. And so we have another class of algorithms called or nonlinear learners. In this case, this is a boosted decision tree or a stochastic gradient decision tree. And if you guys have, if you've messed with Azure ML, there's an algorithm there called boosted decision tree. This is kind of like that, right? So what I am doing is I'm taking the exact same data. Everything's identical. The only difference is that I am, instead of building a linear model, which is, where'd it go? Right here, this is an RX lin mod. I am building an RXB trees, right? I'm passing it the same exact formula, the same training data. I am giving it a few different parameters right here. And this is an important distinction with this algorithm, right? Because this is what we call an ensemble machine learning model. And by ensemble, what that means is that there are multiple models that come together to build this. On the linear algorithm, there's only one model that it creates, right? And it tries to fit a line that fits perfectly through all the data points, and it ends up with being one model. And oftentimes it's not a bad deal. One of the cool things about the linear model is you have some amount of explainability, right? I can tell you how the pickups, the number of pickups in the lag hour 1, how that impacts the model. I can tell you by what percentage that moves the needle. But when we come over to this guy right here, this is almost like a black box. I can't really tell you what's happening inside the process, but I can tell you how it works. So what happens in this particular one, I have defined it to create 50 different decision trees. And they're little small decision trees. So what happens is that the model builds 50 decision trees, and each record gets scored by each of the 50 different models. And the output of each of those 50 models gets averaged together into one score. So it's almost like asking, so if a linear model be like asking an expert what they think the forecast is going to be in 5 hours. The boosted decision tree is like asking 50 different experts what they expect the forecast to be in 5 hours, and then averaging all their answers together into one. Now, here I'll plot this guy real quick. So I mean, I can run the summary for it, but it really doesn't tell you anything. It just tells you some stuff right here, which is essentially all the stuff that I already knew before I built the model. So that's not very useful. But it does have the ability to plot, okay? And so let me talk about this real quick. What we're looking at here is a plot of all the decision trees. On the x-axis, we go from 0 to 50, representing all 50 decision trees. And the y-axis tells us how much error do we have in our model. So when we start with one decision tree, we have a lot of error. But as we keep adding more and more decision trees to this process, you can sort of see the error rate keeps coming down, 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 starts bending around, I don't know, 15 or 12 to 15, it starts to bend, and then it starts to increase at a decreasing rate. It starts to tail off, right? And we go all the way to 50. I could have made this 1,000 or 10,000 decision trees. Wouldn't have been a good idea, but it's certainly I can control the number of decision trees. The point of this graph sort of tells me where additional decision trees don't necessarily add much value. So there's not much of a difference between 40 and 50, or you could argue 30 and 40. I could probably turn this thing off at 30 and still get as good a score as I would have gotten at 50. Very, very close. So the difference between 30 decision trees and 50 decision trees is insignificant. But the difference between one decision tree and 10 decision trees is huge, as well as the difference between 30 and 10 is significant as well. So I do it the exact same way, except for instead of putting it into an LM variable, I'm putting it into a BD variable, right? And then I'm doing the predict. The only difference is I'm putting the predictions in different tables. I'm putting them in _BD, _ train BD, and test BD. And so I'm doing the exact same predict functions. And then if I go back over to here, I can see that I also have a second set of measurements here. So if I run this entire thing, whoops, well, I'll run the linear models to begin with, and we go from a 72 in our test data. But if I come down here and run it for the boosted decision trees, let's not run the truncate. I can see that my numbers are significantly improved. So I go from and here's a scenario where I'm getting a little better score in test than I am in train. But I think that's just sort of due to randomness in the tests and training set. But I can see that my boosted decision tree is significantly better than my linear model, which tells me that there's some amount of non-linear nature to the data. Now I could have transformed the data and did a bunch, maybe a logarithmic transformations or some sort of power transformation to the data and gotten in a little better format for linear modeling, but I didn't. And also, word of the wise, if I've got some really high scores here, if I got those in the real world, I mean, this is kind of the real world, but it's not a model that we're going to be using for anything. I would be very suspicious of those numbers. But I built the same exact model as I did from the linear model, but just doing almost too good of a job. If it seems too good to be true, there's a real good chance that it might be. So just sort of take that with a grain of salt. Okay, so now I've got this really great model, this boosted decision tree that I built. Now what do I do with it, right? How do I use it in any way, right? And this is where historically a lot of data science projects sort of bog down. Because once we build, it's not hard to build the model. It's not hard to extract the data from the database or databases and transform it into a machine learning data set, build the model, do all the transformations, do all the creating feature engineering, all that sort of stuff. And then you end up with this really great model that's highly predictive. Well, okay, I've got this model in R. Now what do I do with it? My users don't use R, right? My users are in Power BI or in some web application or something like that, or a mobile app. Now I have to get that model to them. So the most powerful predictive analytic model, or predictive model in the world is of no use if you cannot put it in the hands of the people who need it when they need it, right? And so this is where our server within SQL Server really steps up. Within Azure ML, you can deploy it as a web service, which is pretty cool. But within our server, I think you can do even one better than that. So I can take my model and put it right in SQL Server and call it from within store procedures. So it's a little bit quirky now because it's still pretty new, but from what I understand, there's going to be a lot of changes coming soon, specifically around usability and that sort of thing. Now, if I want to, let me get there in a second here. I'm going to close a few of these out. So what I want to do is I want to train the model, and I want to put it within SQL Server. Okay. So when I look at this table right here, I have this table right here. It's called R data. And I run this thing. I have a model in this table. This is a var binary max column. So I have literally taken that model, serialized it, stored it within SQL Server. And what's going to happen is every time I need it, I'm going to pull it out of this table, reconstitute it into a model, and score the data. So let's see how that happens. So I have this. This is a store procedure right here. This is called train model RX, right? And this is a store procedure that lives within SQL. There's no RStudio or there's no Visual Studio or R tools for Visual Studio or anything like that. What I am doing is I am calling within my store procedure. I'm calling this guy right here. This is SP execute external script, and all I'm doing is I'm telling it I'm going to pass you a script, in this case an R script, and I want you to execute it and then do something with it. So all I'm doing is I've taken a piece out of my data, right, out of my RStudio, right? I've literally copied it and pasted it over here into this store procedure, right? This is the entire training code right here. So what happens is that I'm passing it in this guy right here. This is the data that I wanted to use to build the model. And then down here, so this is regular old SQL Server, right? I'm pulling it from the view, the same view that I used in RStudio. And what it's going to do is down here, it's going to pass in that as a SQL, you know, as a variable, a string variable for a SQL statement. And then we're going to do some stuff here, which is just all we're doing is we're saying that pickup hour is a factor, and it has values of 0 to 23, and day of the week is also a factor or a categorical variable, and it has values 1 through 7, which can also be read as Sunday through Saturday. So the data comes into this script already set to the variable called input data set. And so all I'm doing is I'm adding this column information to my data set and resaving it over itself. So all I'm doing is adding some metadata to it. Then I have the same model right here that I built. Now, through the R process, I would have probably maybe removed a few of these or changed some things around. And then once I get it set, I'm going to copy and paste it over here into SQL Server. The same exact parameter. So as I'm building the model, I'm going to manipulate these parameters to try to optimize this model building process. And I'm saving it to this variable BD. And then I'm taking BD and I'm serializing it. And I'm telling it that don't worry too much about this. It's a raw serializable value. And I'm converting it to a data frame, which is R's version of a table. And I'm into this variable. And then as the execute script function, the output of it, basically this is an out variable for a store procedure, is essentially the value that's in this guy here. So what it does is it takes that model, I build that model, I read in this data right here, I add some metadata to it, I train the model, I serialize the model as a single value, and then if you look right here, I'm inserting it into models, right? And all I'm doing is the output of this thing right here is going to create a SQL result set that I'm going to insert, a single row that I'm going to insert into this table right here. And so one of the cool things, it's a little bit quirky having to put it in here because it's not a good editor for R, but one of the cool things is it allows you to retrain the model periodically without having to do anything other than execute this thing right here. So if I run this thing, it will retrain the model. So a month from now, when I have more data, I might want to include that in my model. So I want to consider that maybe something is changing in the way people are driving or riding in taxis. So I want to continue to do that. I don't have to go back over to R anymore, RStudio. I can literally just execute this thing once a month, right? I can even have this set up as a job, just retrain this model once a month to consider new data, or once a week, or however often you deem it useful. So now that I've done that and I've added that into our data, I can go over to the predict store procedure. And this is the one that we're going to run on a hourly basis, right? If our goal is to predict demand every 5 hours in advance, we're probably going to want to run this thing on the hour every hour and predict and make an hourly prediction. And all we're doing here is this is a second store procedure with some R code in here, right? And I'll talk about this in a second. It's this predict right here. All I have to do is predict with an inquiry, right? And my inquiry in this case is going to be the data. And now, in theory, this is all the data, but I could, like I said, this is configurable. This is a store procedure. I can do anything I want. So if you guys have done tons of crazy stuff with store procedures, I can just every single hour I can grab the latest hour. I can put this in the scheduler, in the job schedule, and just run it every hour. And so what it does is it brings in the data. So I go to my model table right here, my models, and then this is just sort of some short code to get the one entry in the models table. And I'm setting it to this variable, which is a var binary max. And then I'm pulling it in through these variables right here. So it gets into the script right here, right? So then I convert it to raw, and then I unserialize it into this right here. It becomes an R boosted decision tree once I do this, right? And then again, I'm also setting the column, the metadata for those particular columns. And then I'm applying it to the data set. And then now I'm doing a score, right? So I'm scoring the variables, the data from the predicted model. And this is giving me all the scores, and then I'm converting that to a data frame, like I said, which is an R table, and then putting into this output data set, right? And that's what comes out of this store procedure right here. And then I'm inserting it right here. I'm inserting the output of this execution into this table right here. And so I could do this, like I said, once an hour, once a day, once a second, whatever. It's super fast. And then what ends up doing, it ends up getting into these tables right here, in which this is the BD. Let me refresh this, which would be this guy right here, right? So this is the output of the execution, right? It's going to give me the ID, which is related to the particular hour of the particular day. And I just brought over target pickups because this is the actual and this is the forecast, right? So it brings it all over there. So I have this table now, and I'm going to come over to Power BI. I'm going to read those tables because it's a little easier to visualize the data than it is to look at a metric or to actually look at the data itself. What we're looking at is the pickup data by hour for the entire year of 2013. It's a little messy, so I'm just going to narrow it down to an individual month, right? And what I'm seeing is a pattern in the data, right? If you're doing a forecasting problem and first thing you want to do is visualize that data and see, does it look like there's any sort of pattern in the data? Is there a trend? Is there any seasonality? That sort of stuff. And clearly there is, right? Which tells me this is going to be a relatively successful forecasting project. So I'm seeing this data. This is all the up and downs, right? This is the data before I do any forecasting. Now I want to go over to the forecasted data, right? So I built the model on January through October, and I'm going to use it to see how well it forecasts the data for November and December. So that's part of the test or the train and test separation. So our training data was January through October, and then our testing data is going to be November through December. Now, in theory, if I'm doing any sort of calendar forecasting like this, I really want about 3 years worth of data so I can see the different patterns for the particular months of the year. I would expect certain months to be much more taxi, more demand for taxis than others. And if you're doing sort of seasonality, year by year seasonality, you'd like to see 2 to 3 years worth of data. But we only have 1 year, so we're sort of limited in that situation. So this is a lot of data. I'm going to sort of focus on a particular week of the year. So this is week 46, which happens to be in November. This is the actual demand. These are how many pickups occurred. Now what I'm going to do is I'm going to add the forecasted demand from the linear model. Oops. And then you can see the linear model is the black line. You can see this is the one where it was around 72 was our metric, 72 out of 100 or 0.72 out of 1. It's pretty close. It's not perfect. In the real world, this is probably going to be good enough, but we're doing a demo here, so we want to one-up ourselves. Now, if I take off the linear model and put on the boosted decision tree, remember we got a much better score, and you can see how much closer it approximates the actual demand. And remember, we're doing this 5 hours in advance, so it's not going to be perfect. We're going to have some misses and stuff like that, but for the most part, it's fairly accurate. So let me kind of summarize this up, and we'll take some questions. What really makes this cool, in my opinion, is the ability to do all your work here in R or whatever it is you want to do. This is going to get messy, right? We're going to do a lot of different stuff. We're going to try a lot of different things, and when we settle in on a model, we're going to drop that model into where do we go? We're going to drop that model into a store procedure, right? And really, all we're doing, we had 2 big pages of R code in RStudio, but all we end up with is just a few lines here within our model. And again, what really makes this cool is the ability to execute it right within the data. I don't need to move the data out of SQL Server to execute a model. But what really happens behind the scenes is that we're executing an external script. So we're not doing it within the SQL runtime. We're doing it within another managed runtime that's managed by the SQL runtime. And if this thing blows up, if I do some crazy thing in here that just kills it, it's not going to impact the SQL server. It's only going to crash the R executable and not the SQL server. So you won't have to worry about bringing a production database down. Now I'm sure there could be some security risks with external script, and we'd have to go with Microsoft to see how much damage we can essentially do. Okay, are you there, Devin?
Yes, I am.
All right, you want to read some of the questions in there? I can't necessarily see them here.
Okay. One of the biggest questions we've been getting is where to find this data on the internet. Is that something you can share?
Yeah, I got it from Microsoft, believe it or not. But you can get it from Kaggle, you can get it from Microsoft. It's somewhere out there in Azure. I forget. It's a link. If you Google, I'll find a specific place where I got it, and we can share that with the email list. But
Yeah.
you can also just Google taxi data 2013, and it'll show up.
And there were a couple questions about asking where you can watch this webinar again. We will be posting it on our Wistia page so you can see it again, and we'll go ahead and add the link to where Jason got the data. We'll add it there. Another question we had, do the RX functions support the nonlinear regression tools in R on SQL Server, or would that need to be done locally?
Read that one more time, the beginning part.
Do the RX functions support the nonlinear regression tools in R on SQL Server, or would that need to be done locally? There's a second part to it.
So,
more generally, do you find there is much advantage in using nonlinear equations in real-world data sets?
So the answer to that one is yes. They'll tell you, the experts in the world will tell you that there is no such thing as a free lunch in predictive analytics, meaning there isn't one particular model that you can always use. You need to try all the different models. You need to try the linear models and the nonlinear models, and let the model tell you which one's most appropriate for the data. That being said, when you're dealing with linear models, you have to have well-behaved data. You have to have data that's somewhat normally distributed, cleaned up. Oftentimes it helps to have them normalized, that sort of thing. When you're dealing with, like, for example, a boosted decision tree or some of the other gradient boosted models, you don't necessarily have to clean up as much data. So, for example, the boosted decision tree is kind of like lazy man's modeling tool. It's very, very good at taking messy data and making sense out of it. So, time so if you need to build a model where you have to be able to explain what's happening in that model, you're going to want to use a linear model because those are the ones that you can explain. If you're more interested in ability to get a much more accurate or a more accurate prediction, then you're going to include the nonlinear models that are essentially like black boxes, like a boosted decision tree or a neural network, right? You're not going to be able to explain how it came up with the answer, but you are going to be able to test how accurate that answer is by comparing it against comparing your model against test data. Now, that doesn't mean the nonlinears are always the most accurate either. Sometimes linear models are the better model. It just depends on the data that you're dealing with. And you always want to use two models being somewhat close in performance. You're always going to want to go with the more simpler model, right? The simplest model is always going to be the best, provided that it's somewhat comparable in performance. And you can use any, so I'm using the RX functions within SQL Server. You can use any of the R functions within R Server, within SQL Server. So it doesn't have to just be the RX functions, but what the RX functions allow you to do is they allow you to address a much, much larger amount of data. So if your data is only, a few hundred megs or even a couple gigs and stuff like that, and you've got a particular algorithm that's not within the RX family, by all means, you can use like the extreme gradient boosting or XGBoost mod or package is super popular for modeling specific kinds of data, and it has its limitations, right? You can only fit as much as you can, much data as you can in memory. And now remember, you're doing this also on SQL Server, so typically the SQL Server is going to have a lot more memory than your client will have, and of course your R runtime is only going to have access to a certain amount. So if you have 50 gigs of RAM on the server, R is not going to be able to consume 50 of it, right? So it's going to be relegated to a certain amount. But depending upon what you're doing, that'll be configured accordingly.
All right, next question. Do you have a suggestion for an entry-level guide to R?
There are a ton of things out there. There's a lot of free stuff out there, and R has become very, very popular. It's really like one of the most, it is the most popular programming language within statistics, right? Python is a very popular language too, but it's a general purpose programming language. It does have a lot of hooks into machine learning, but R is specifically focused around statistics and machine learning. There's a lot of free information out there for R. We are going to be developing an R course soon, and with that I'll be doing a lot more sort of R specific webinars, but there's a lot of books. If you go to like edX, Coursera, there's a lot of other sites out there. There's stuff that you can do. You can take their courses without actually paying. You don't get the certificate for it, but all you learn. There's a lot of books. It is one of the good things about going with it. Microsoft is on board with R, obviously. When that happens, there becomes a lot more information and access to that technology. So just like go to Coursera, go to edX. They'll have free classes you can take.
I just wanted to add to that Evan suggested The Art of R Programming by Matloff is a great place to start. And our next question, which is probably going to be our last, do all of the learning algorithms available in R merge into SQL Server, or just the ones you demoed today?
No, that you can run virtually every single one of them and within SQL Server. Again, if you're not using an RX function, you're limited to the amount of data you can process. That's the big difference between the RX functions and all the regular algorithms that you can pull down from CRAN, all the different packages. We probably have time for a few more.
Okay. Is it possible to use different libraries with SQL Server and R, like MAS or CRAN libraries, and can this be used for classification?
Yes, to both of those. You can bring in any library from CRAN or even from GitHub, some of the dev tools type stuff. And what was the second part of that? Oh yeah, classification. Absolutely, you can do classification. That's just a different kind of forecasting.
Is there a plugin required to set up the connection from R to SQL Server?
No, you just need you need to install SQL 2016, and the R there's a when in there like where you would normally install like SSIS or SSAS, you can install R server now, as well as you would install that on the server, and then at your client you can install the R standalone tools. It's all part of the SQL Server installation.
All right, and this question. We have a data scientist who is very well versed with R. With R services in SQL Server 2016, do they have to learn new syntax? Can you use regular R syntax and all the packages available and still use the scale R and multi-threading of SQL Server 2016?
Yeah, so most of it you're going to be able to use. You're going to be able to reuse your code. If you're going to use the RX functions, there's a little bit of a different, it's just like learning a slightly new syntax. It's not learning a whole new process. It'll be something that somebody in our program would pick up in a day. It's not a significant investment to make that leap.
All right, last question. We'll try to keep it quick. The pickup hour lag 1, 2, 3, etc. values you created. What are the pros and cons to pre-creating these values the way you did versus having a tool or system to do this automatically, assuming it can?
If you had something that could automatically create those for you, then by all means do it. It's just one less step that you would have to do as a developer, but that's not something that's always available. I happen to know that lags just are a very useful thing when forecasting time series data, because you're trying to predict the future based on the past. So you're going to see that. You may want to do a Fourier series in there as well, which is sort of a little more advanced signal processing terms. But typically, if I'm going to do any sort of a time series forecasting, I'm almost always going to, what I'll do is I'll generate, depending on the time frame of the problem. I mean, this was a 5-hour thing, so I wanted lags that were specific to hours and even days. But I'm going to create a whole bunch of lags. Originally, when I did this, I created about 20 different lags at the day and the hour level, and found out that most of them weren't useful. So I dropped them off. I didn't need them. So that's part of this data science or exploratory data analysis process, is trying to just figure out what's useful and what's not. And then so once you sort of narrow in on that, you get a little, you can sort of drop off a lot of that stuff that you don't need. And again, the less stuff you have in your model, the simpler your model is, the better. But obviously it has to be, it can't be too simple or it won't be useful.
All right. Thank you, everybody, for joining us today. And once again, we will have this webinar up on our website shortly. Jason, thank you for your time. We really appreciate you and your knowledge.
All right, guys, thanks a lot. I appreciate it.